Okay. Hello, everyone, and welcome to JuliaHub's latest webinar, Calibrating Models to Difficult and Noisy Data with JuliaSim Model Optimizer. I'm Misha St. Amand, the head of marketing for JuliaHub, and I'm here to moderate questions and just kick things off. I'm joined today by our presenter, Dr. Ranjan Anantharam. Ranjan holds a PhD in mathematics and computational science from MIT. At JuliaHub, he helps customers leverage modern computational methods using JuliaSim, and he serves as a sales engineer and a bridge for customer success at JuliaHub. So that all said, I will hand things over to Ranjan.
Thanks, Misha. Hi, everybody. Thank you for joining us today at this webinar. This webinar is all about calibrating models to data, difficult and noisy data. And the way we do this is through our module called Model Optimizer. And this is, of course, part of our JuliaSim modeling and simulation suite, which I will get into. But first, for folks who don't know who we are, just as a little primer, we are a team of Julia programmers primarily. So we are all contributors to the ecosystem or to the Julia programming language. So Julia is a language that tries to give you that tries to match the performance of a compiled language or a sort of a compiled low-level language like C or C++, while keeping while feeling like a scripting language. So sort of keep this code size to be as small as possible. So you see that Julia here is on the bottom left here. And so it tries to strike that balance between productivity and performance. In Julia, one of the key open source packages is a package called differential equations.jl, which is a suite of very fast differential equation solvers, best in class, some might say, which is about an order to 2 orders of magnitude faster than most other software suites out there. Has been developed over a number of years at UC Irvine, at MIT, and at the Julia Lab, and currently finds a home within the SciML open source ecosystem. But really, what we do is we are a company that's built off the open source. So right at the bottom there, we have this foundation of open source packages, including the differential equations packages that I mentioned. Along with a bunch of other packages that, from a variety of other disciplines. But what we as a company do is we've built this cloud platform that goes on top of that called JuliaHub. So this is a platform which is meant for all things Julia. It's a secure, validated, reproducible platform. It's a platform where you can get on-demand compute. So you've built a large model and you want to simulate it. You can then launch a job on JuliaHub, which allows you to leverage a large amount of compute in a very, very short, very quick time frame. So on top of this cloud platform, which is our proprietary cloud platform, we offer a bunch of different products. The one we're going to focus on today is JuliaSim, which is our modeling and simulation product, which handles physical and multi-physics simulations. So JuliaHub as a platform is again meant for on-demand compute. Is meant as a place where you can store all your data sets, load your proprietary Julia packages and registries, spawn up notebooks, have a Julia interactive environment, and to be able to bring all of the elements that you love about Julia together on one platform. So we're AWS based, as you can see. But really, the reason we're here today, the thing we're talking about today is not the platform as such, but the software suite that's built on top of the platform. So you'd see most of the benefits that I mentioned earlier are leveraged by our modeling and simulation software, JuliaSim. So JuliaSim is again built upon the open source, as most of our products are, but it has a specific design language called Modeling Toolkit, which you will get a sense of through this webinar. To be able to quickly build up your models, we have a large standard library of standard components. Some domain-specific components in there. One of the most exciting ones are the battery modules or the HVAC modules that we're developing so far, which allows you to quickly build non-trivial systems from scratch. And then, of course, when you want to simulate them, you then spawn off a job on our platform. But again, like the software itself helps you do a bunch of interesting things once you've built the model. To tell you what those interesting things are, you can design these models, you can build control systems of these models, and you can build surrogate models. But today, what we're going to do is we're going to presume the existence of a model and a experimental data set that you want to calibrate your model to. So given that this data set and the model, you can do two things. You can sort of calibrate this model to the data, which is a sort of essentially a parameter estimation process, or you can then just use this to discover new physics in the model. So basically, what you would do is you would sort of augment neural network terms to your model, train those neural network terms, and then sort of reinterpret those neural network terms from a basis of physical terms that you've a priori decided. So these are the two sort of main modules here in our JuliaSim Model Optimizer. So well, essentially, you can take a dynamical system and then sort of calibrate it to data. And the way you would do this is via two main pillars. One is a suite of calibration algorithms, these are sort of these calibration algorithms that we've designed to help you avoid local minima. And each calibration algorithm can be composed with a suite of optimization algorithms. And I'll get a little bit into what the difference between a calibration algorithm and an optimization algorithm is. You can basically compose both these components together to be able to come up with different strategies to avoid local minima. Of course, all of these things tend to be very problem specific, which is why we've tried to make trying various combinations very easy in the software module. So yeah, so that's how we use both of these. And other thing you can do is, supposing you have data, but you have multiple parameters that can fit that data. Then you have some sort of uncertainty as to what those parameters could be that fit the data, and we allow you to capture this uncertainty along with using this module here called parametric uncertainty quantification. Usually, this tends to get used when your models have issues of identifiability. So, for example, you have two parameters, P1 times P2 that is present in your model, and you could have different combinations of P1 and P2 that can fit your data. So this tends to not be the case in a lot of physical models. I mean, there are plenty of examples, of course, but this is definitely true of a lot of biological models. So we might not really get into this today, but if you are interested in this, I can point you to alternate resources on how to understand this, as well as the documentation. So once we go through calibration algorithms and optimization algorithms together, we will then look at model discovery and really see how you can capture unknown physics using JuliaSim Model Optimizer. So these are the two main modules that we're going to cover today. So as I said, this module presumes the existence of both a model as well as data. And so once you have both of those together, you can then try and get good predictions out of that. One example of where you might want to do this is you've built a physical model, but then you want to validate your physical model. And the way many domains tend to do that is they get experimental data and then validate and then train and then tune the model to that experimental data, get new experimental data, and then see if you can, which is called validation data, and you sort of see if your model can match the validation data. This is the sort of workflow is common in many domains. Anyway, so let's get into the first module, so which is model calibration, right? So as you see, Model Optimizer gives you a bunch of robust calibration methods that try to exclude local minima. These usually tend to be multi-objective, and we'll get into that a little bit, how exactly that happens. But before we do, to sort of appreciate why we made these choices, I need to tell you why model calibration could be hard, and there are sort of two main reasons. So one is, of course, the fact that you have highly nonlinear models, that often tend to be very high dimensional. if you're using a model paradigm, like many, when you use different types of modeling paradigms, you tend to be you tend to build these models using using physical understanding, which and then rely on a compiler to generate the actual dynamical system for you. And the resulting dynamical system could be highly high dimensional and nonlinear. So it's very easy, like using many sort of paradigms such as, let's say, Modelica, to be able to very quickly generate these high dimensional nonlinear systems. And these, of course, tend to be very slow to integrate, even with state-of-the-art solvers. And of course, because it's highly nonlinear, the parameter estimation can run into many local minima. And of course, like that's one part that's hard, or let's say that's sort of a thing that you have to deal with. The other thing you have to deal with is sensitivity analysis methods. These also can get very unstable when system models can get highly nonlinear. And so you need a nice way of handling this. And of course, this gets even more complicated when you have models that sort of have known time domain instability. Like, for example, if a dynamical system is unstable and open loop, right? And and if your model has discontinuities, and there are many examples across different domains where this is true. And we'll look at the time domain instability aspect in this particular webinar as well. All right. So how does this deal with that? We use, of course, the best-in-class integrator, so that every iteration of your parameter estimation is as fast as it can be. Could be GPU accelerated in many cases as well. And we provide, and of course, we can't guarantee that you won't run into a local minima, right? But we give you a bunch of different strategies on how to avoid them. And of course, then we'll get into all of these calibration strategies in a second. So the other thing that we do is, when you have time domain instability, we use what we call a special calibration method called a multiple shooting method, and we'll get into that in a second. But really, this is like a particular type of case which we do handle. And if you have time domain discontinuities, there's the sensitivity analysis methods that allow you to get derivatives in the case of jump equations and things like that, and like hybrid equations, which are also sort of implemented on the hood. And what's nice is all of the secret sauce is abstracted away from the user. Some of it is open source, so you can actually go and look at it. But most of it, the secret sauce is given to you in a manner where you really don't need to worry about this. All you need to worry about is the model specification and the data specification and the things you want to calibrate to what. And the aim of the module is to hide a lot of these things from the user. Okay, let's take a second, and let's start by telling you what exactly a calibration algorithm and an optimizer is. Just so, by the way, feel free to interrupt me with any questions. I know that there's a lot of detail here, but feel free, and I'm sure Misha here will let me know as well. But again, so let us sort of draw a contrast between a calibration algorithm and an optimizer. So a calibration algorithm is essentially a loss function formulation, right? So how exactly do you specify the loss function, or what is the sort of L2 loss function that you're going to train over? And of course, like, so as they say, there's many ways to skin a cat, and this is sort of like, I'd say, aligned in that direction. But then each calibration algorithm can, as I said earlier, be composed with an optimizer. So an optimizer is your standard notion of an optimizer, which is sort of an iterative numerical scheme that sort of helps you converge to a local minima, right? And in this module, all these supported optimizers are encapsulated in optimization.jl, which is again open source and sort of encapsulates a number of gradient-based, gradient-free, Hessian-based, or global optimizers, or many of these meta-heuristic algorithms as well. So all of these are encapsulated in this, and you really can compose all of those optimization algorithms with our calibration strategies. And of course, these calibration strategies are closed source, but I'm going to give you a flavor of what they are now. All right. So the first calibration strategy is a standard calibration, which is sort of our default. We call it single shooting. So what you need to do is specify a P, so an upper and lower bound of your parameters that you want to optimize, and you have a sort of Cartesian space of parameters. And what you try and do is try and match a prediction, given a prediction for a parameter, you try and and you try and solve the system, and you see if the solution matches data. So this regular U here is the solution given by data, and this U solver is the solution that you've estimated. And of course, you try and take some sort of functional across the entire time domain, and this is really what this is really what the estimation problem is trying to solve. And of course, the standard way to do this is as you might know, is an adjoint method that lets you get the gradients of a functional with respect to many hundreds of parameters, and and so this uses a different a specialized adjoint method depending on whether the model is a hybrid equation or things like that. So all of this again is under the hood. So to give you a sense of this, let me just pull up a demo. So this is a model of a system of coupled clutches. So you see the 3 clutches over here, and you have 3 rotational inertias, 4 rotational inertias really. And each of these clutches are controlled by a particular input. So there's a sinusoidal input going into this clutch 1, and there's a step input going into clutch 2. And what we're going to try and do is, given some data and given some data of how the system might have to operate, we'll try and tune, this kind of we try and tune these 2 inputs to match, the desired system behavior. So let's go ahead and do that. So before I do that, just want to quickly check if I have any questions. If not, I'm just going to go ahead and start the demo. So let's go ahead. So the first thing I want to show you with regard to the demo is this is JuliaHub, the platform. This is how once you log into JuliaHub, you will be able to get an interface like this. You have applications, which are these prepackaged sort of these are prepackaged sort of modules that we provide. And these modules are all sort of connected to cloud instances. So we have a bunch of different applications in here. What you do is try and you launch the application that you need. I already have a Julia application launched here. But again, like there's other things you can do here. You can go through your suite of applications. You can look at the job list. So you see there's a preview of my job list over here. You can look at your data sets, launch a Pluto notebook, and look at your files. And we also have this other really nice thing called projects that's still in beta, but it's a way for you to collaborate with the rest of your team. If you're interested in something like this, a collaboration tool, do let us know, and we'll get in touch. All right. So this is the platform, and what this version of the platform is going to give you is, let's try and make that a little larger and give you a sense of how the interface to this module looks like. So let's get rid of this plot. Don't give the story away too quickly. So this is how you might interact with JuliaSim Model Optimizer. So you again load your libraries. In this case, I'm gonna load the optimized parameters. So for demo purposes. But in this case, this particular model is actually what we call a functional mockup unit. So functional mockup unit is an open standard where you get to where basically you can define a model in a particular programming, like in a modeling paradigm, and then you can export it as a binary, with all of the model information hidden, but it's a sort of a runnable binary that can then be imported into another simulation environment and then run. So, for example, this particular this binary was exported from a different software, but it's now loaded into a Julia environment. So one natural way, for example, to get started on the platform is to be able to generate a functional markup unit of your model, and then to be able to hand it and then be able to load it in the platform and then use the software. All right. So I first load the software, and the next thing I do is get some data. So as I said, this module presumes the existence of data as well as a model, and we'll take a quick look at this data. Yeah. So as you can see, this data is very dense. It's actually a scatter plot, but this data is super duper dense. And you can see the dynamical system. We are blessed with dense data in this example, but not always, right? And we'll show you examples where we're not. But yeah, we have a lot of dense data here of two states or two observables that we want to calibrate in our system. And so,
Ranjan, excuse me, we did get a question, which was a request to give us the paper the calibration algorithm is reported. I'm assuming that's the, I'm assuming we can include that when we do our follow-up emails.
Yeah, so I mean, this is a, so let me just answer this live actually. Like this is, the single shooting one that I presented to you is actually a very sort of standard parameter estimation formulation, which is why it's the default. It's just a way of calibrating like the time series, like a time series to a model, right? And that, in some sense, is like you'll have to go to the maybe the 1960s or something like that for a standard sort of paper looking at that. So if you just Google adjoint sensitivity analysis, you'll look at the you'll be able to get a list of you'll be able to get this formulation as well as how you get the derivatives and things like that. So that's a good resource to check out if you're curious on an academic sense. In an academic sense, how exactly we do a lot of this stuff. So that's a good useful resource. I'd say, yeah, but of course, like there's a lot of interesting nuance with how you implement it. Most of the nuance there is what we sort of maintain as proprietary. But the standard open formulation as such, the problem formulation as such, you can find in the literature out there. I hope that answers the question. Okay, so now that you have model and data and we've looked at the data, let's load this data into Model Optimizer. So the way you load data, the standard way to sort of load data is through this object called an experiment. And an experiment is an encapsulation of for data in a model. So basically, well, I've conducted an experiment. I've gathered some data, for that experiment, and and JuliaSim sort of records a data set as being associated with the model through this experiment object. And so now we tell the experiment object that this, that it has a particular time span, and and we have a particular tolerance at which this data was generated. Of course, these are all optional arguments. You don't need to specify that. Let's say this is actually setting up an experiment. Oops. So let me show you what that looks like. So you see this, you have a nice little experiment object that gets encapsulated on the command line. The next thing you need is an inverse problem, because now JuliaSim Optimizer knows that there's data and it's associated with the model, but it has no idea what the parameter estimation problem is. So we have a standard way of specifying these parameter estimation problems called inverse problems. And the way you do that is again through this thing called inverse problem. You provide the experiment, you provide the model, and then you get the quantities along with a search space for these quantities that you want to estimate, right? So that's what's being specified in this particular line. And then again, like you get this nice, pretty explanation. You have a inverse problem for a functional markup unit with with two parameters, and you see that here it says one experiment, right? So you can have multiple experiments. You can have more parameters. You can have different models, and all, and the model optimizer is extensible in all these different dimensions. Now, to actually do the model calibration, you need to specify two things. Actually just one thing, which is the algorithm that you want to specify. Here in this case, we're doing the standard single shooting algorithm, which lets you you tell it, you run it for a max number of iterations, and we use this this optimizer called LPFGS, which is a sort of standard gradient based optimizer that you can find out there. And then once you specify both these things, you can then run the calibrate function using this algorithm object, and then you will get an answer. So for the purposes of this demo, I've loaded this up. This takes a couple of minutes to run. And now once you've loaded up the result, you can see it's a little bit difficult to see, but there's a line here that corresponds to the prediction, and then there's a bunch of tiny little dots that correspond to the data. And because the data is so sensitive, it's so dense, it sort of appears line over line, as you can see here. But yeah, that's how you run a standard single shooting algorithm from Model Optimizer. And so this is one of the this is a standard way to use the tool. All right. So this is when everything works as expected, right? But then let's go back and look at the scenario where, what if you have time domain instability, and how exactly might you want to deal with that? And so one thing, one sort of feature of this is you can't integrate completely in time. So if you look at the previous formulation, you've integrated from the initial condition at time equals t0 all the way to the terminal time equals capital T. But in this case, perhaps you cannot integrate the model completely from t0 to t. And that again might not be true for, let's say, one parameter, right? But it could be true for any of the parameters in your search space, right? And of course, this could be there could be a reasonable physical explanation for this. Usually when this happens, a standard recommendation is to perhaps check your model and see why it's unstable. But in many cases, it's sort of well known to be unstable. So some loops, some dynamical systems tend to be unstable in open loop, but with feedback control, they can be made to be stable. Right. So how might you handle this? A standard way to sort of do it, or let's say, won't say a standard way, but the way we do it is we divide the system, or the time integration domain, into multiple time segments, right? So multiple time segments, and so let's say we have about n of these, a small n of these, and what we do is we run the same problem, we run the same optimization problem in each of these time segments, and because they're all independent, you can do them in parallel, and we do this auto parallelization under the hood, by the way. Again, in a manner that's completely abstracted from the user. You'll see how. And once you do all of these optimizations in parallel, you need to make sure that the tuned or the trained trajectories matches at the points of discontinuity, right? So what we do is here we impose a continuity penalty. So basically, if let's say you have two time segments, the end of the first time segment should be equal to the start of the second time segment, which is basically what this says. And this is just a generalized, n time segment version of what I'm saying. So really, this might be a lot sort of a long formulation, but really it's just two steps here. And then what you do is, well, how exactly do you find these time segments? And the answer is you don't. You sort of add these and you optimize along the way, right? And so at the end of the optimization process, you get a set of parameters that fit the data, as well as the time domain segments that the time domain has been split into, which is quite interesting. So it gives you a sense of where exactly the model is unstable and everything. Okay. So the main thing you do have to do here is choose how many time segments that do you want to use, and in many cases, we have a parameter for this. So usually the way I'd like to tell customers is to choose a low number and then sort of keep increasing it, or do as many as you dare, and in terms of your computational bandwidth. And once you do that, you'll get a you'll have a you can then look at the result and see if it's a reasonable fit. And if it's not, of course, there's some more instability you need to deal with. And of course, like how exactly do you ensure a continuous solution? You impose this continuity penalty. One of the things that we're working on is to instead of having this as a penalty to impose this as a constraint. But currently, Model Optimizer imposes this as a penalty. Okay. Next.
Ranjan, before you move on,
yeah.
there was a question that came in just a couple minutes ago.
Yeah, let's do it.
And the question is it only possible for model exchange FMUs, or can it also work for CoSIM FMUs? What are the minimum versions? Yeah,
sounds good. So we support both model exchange and co-simulation. That's the answer to the first thing. And we usually support 2.0, although we have some work to support 3.0. But yeah, it's mostly 2.0 at this point. Yeah, and of course we support both model exchange and co-simulation. But this is just as an example I pulled up model exchange here. Okay, I also see another question because I have this questions tab open. Does the number of time segments relate to the number of discontinuities? Well, it's usually hard to tell. The way to think about it is that you might have this generally is not. This is a little bit orthogonal to the notion of discontinuity. It's mostly, well, if you actually just look at the question on the slide, right? If I give you a physical example, perhaps this might be very clear. So this is an example of a ball and beam control system, and so basically there's this beam, and this beam there's an angle phi to the z-axis, right? And there's a position of this ball, relative to the end of the beam called x. And now there's a controller that tries to balance this ball on this beam, right? And there's a certain amount of friction, there's gravity, and so on and so forth. So now this system is quite unstable in open loop. So as you can see, this ball can roll off the beam very easily, and that in some sense is one of the reasons for the instability. In this particular case, as soon as it rolls off, yes, that is a discontinuity, because that is an event. But in many cases, even when the ball does not roll off, the system tends to be unstable. So I'd say this is somewhat, related and orthogonal. And of course, if you'd like to discuss more, do get in touch. We can look at it. We can discuss your model in detail. Okay. I do see one more example. So this is also related. So I'll just take this. Which DAE methods are implemented in Julia? Well, and do you recommend this for parameters? Yes. So to look at, we have a bunch of let's say open source different DAE methods. So if you look at Modeling Toolkit, the standard way we sort of do it is we get the model, we do an index reduction, we get this as an index 1 DAE, or in some cases you might want to convert it to an index 0 mass matrix, ODE, and of course, like the ODE solvers are completely there, are like a huge variety. But then we also support DAE integration as well. So all of these, let me just point this out in the documentation. So let's grab a few. We can follow up with some links to documentation on this. But yeah, there are a bunch of DAE methods that are implemented in Julia. We also have some DAE methods that are implemented and are proprietary, that are part of the package. In many cases, sometimes we leverage those. We don't have a lot of I don't know that we have a lot of public documentation on that. but we can tell you about those methods if you're interested. Those methods are specifically set up to handle discontinuities, implicit discontinuities in time. But we can set that up for you if you'd like. Do get in touch with us. But yeah, as for the other DAE methods, I'd say there's plenty of links on the open source, and we can send them to you. Right. So thanks everybody for the questions thus far. So what I'm going to do is perhaps show you a little bit about this model. By the way, this particular model is available as an example on our documentation as well. So you'd see a unstable dynamical system. There's some questions on why exactly this is unstable. This is sort of a standard, one of those standard motivational examples for feedback control. So if you just go ahead and just Google ball and beam control systems, and you'll get a lot of interesting material out there. Whoops. There's a lot of interesting resources out there that explain to you why the system is unstable in open loop. So one way you could do that is go to like an unstable fixed point, do a linearization, and look at the eigenvalues. That's one way to convince yourself. The other way to convince yourself is to have a nice look at the system equations, which you can do. But really, like what part of it, I'd say like the quick and dirty explanation is the ball can roll off anywhere, and that's not good. and it rolls with acceleration, right? Because there's gravity. So that's also part of it, right? So to stabilize it once it starts rolling is kind of hard, So with that, I want to get to the modeling toolkit aspect of the JuliaSim Model Optimizer aspect of it. Again, loading a bunch of packages here. I'm just pulling up some loaded results, but again, so what we are doing here is again pulling the data. You've seen this before, and then we do a little bit of housekeeping. I'll get into what this housekeeping is later. We can, this is a bit of detail that perhaps we can go into at the end of the presentation, or I can point you to the documentation. So the first thing you might want to do is define the model equation. So let me quickly pull up the documentation to show what the model equations are. It turns out these are the two model equations here, as you can see. And there's plenty of this is derived out. There are plenty of resources to see how these are derived. But I'm going to quickly move on for the purposes of time to look at the actual model optimizer portion of this. But again, now we've defined this dynamical system, which simply enter the two equations in there, tell what the observable is, which is the ball position. What position does this come into to rest, right? And that's kind of what we're trying to estimate here. And actually, what we are actually doing here is we're pulling data for how this model, for how this unstable dynamical system behaves, and then we're trying to use Model Optimizer to then tune an unstable dynamical system to unstable behavior that we've seen from an experiment. So that's kind of what we're doing here. But again, to start out, you need a model, which is what we've specified. Structural simplify does the index reduction and many other algorithmic transformations here. For documentation on this, I can refer you to the modeling toolkit documentation. The other thing we do is we add dummy derivatives to the system. Dummy derivatives are basically a way of converting a second order system to a first order system. So I'd say a bunch of housekeeping. But then once you do all of that, you can then define your experiment, which takes in your data and your system, which is nice. And then once you define the experiment, you define the inverse problem. Just like before, the specification is largely the same, right? And you say these are the two values that you want to estimate, and and then you define the inverse problem. This is a ratio of constants actually, and this is a particular force function. a scalar force function that again we're trying to estimate. If you're curious as to what it means physically, but once you do that, now let's start specifying our multiple shooting algorithm, right? So the multiple shooting algorithm, in this case, we'll run this for a number of iterations. We specify an optimizer, excuse me, and what we do is we run this thing called an ensemble algorithm. So this ensemble algorithm is a way of telling the environment, hey, I have multiple optimization problems that I'm trying to run in parallel. So what do I do to sort of run this in parallel, right? This function or this sort of object ensemble threads lets you tell the environment that it should split these up amongst multiple threads. So again, like there's literally nothing you need to do to parallelize this thing. You just need to say multiple threads and we'll do it with multiple threads, which I think is pretty neat. So all the parallelism and all the performance that you want to get from the system is completely abstracted away from the user, which is a huge convenience. You can also optionally specify a maximum time. So you want this to run for, in this case, 40 minutes. And again, this last thing is a must to specify. You need a guess for the number of segments you want to split this into. So we're doing a very sort of conservative 500 because of the instability of the system. And then once you specify this, you can hit calibrate. All of this works out. You see if you scroll all the way down, you'll see a calibrate. You'll see a multiple shooting method defined with all of these solution parameters, or these calibration parameters rather. And now once you're done, you can then call a specialized plotting function, which should load up in a second. Whoops, what's going on there? You should have, whoops, let's see, taking a minute experiment. Let's try this separately. But anyway, I'll pull up the plot for you. But once you have the experiment, let's try and maybe load that experiment from data in a second. And let's try that again. Perhaps this will just do it for us. But yeah, so what this plotting function does is it tries to show you all the different segments that. Okay, for some reason this is not pulling up. So I'm just going to show you this from the documentation. Maybe I didn't save my my plot properly, but really this is what you'll expect to see. So you would see a as you see the data here is done in a scatter plot, and you see the solid line here is your original data. And so what this plotting function does conveniently is to be able to stitch all of those points together with the continuity constraints, and then you see that with this you're able to plot and look at the results. Okay. There's another aspect in this tutorial with regard to uncertainty. I will leave that to you guys to take a look. And this is again has to do with the parametric uncertainty quantification that I mentioned earlier during the session. And this is again, if you don't have model identifiability, then there's a way to capture that using an uncertainty. So if you have multiple parameters that again fit this data, can you then sort of capture the uncertainty with respect to parameters? All right, so that's our second demo. Okay, and so again, that's multiple shooting methods when you have time domain instability. But then there's one thing that you might have noticed here that I might have that you think I might have glossed over, but not really. There's this thing took like 44 minutes to run, right? And to some extent that is again natural. If you spin up a beefier machine, this thing will run faster. And sometimes many of these parameter estimation problems run multiple times, right? Or need to run sort of for a fairly long time, to be able to run to be able to run well. But there is a thing to note here, which is sort of just a consequence of the algorithm, right? So the reason like this number is not that surprising is if you sort of look at the algorithm, the way you would compute derivatives. Let's pull up that loss function. Yes. So the way you'd compute derivatives is, again, as I say, you run this adjoint sensitivity method. And what that adjoint sensitivity method does is it does a backwards integration from capital T to T0. So the computational cost of computing the derivatives of the system is on the same sort of order of magnitude as solving the original system yourself, right? So this means that you're spending you're spending two solves in some sense, the computational cost of two solves every iteration, right? And that's why these things can get quite expensive. Of course, like in many cases, you just, it's something you have to live with, right? And there's not much you can do to amortize that. But you could use an alternative algorithm, which is this third algorithm called the collocation method. And these collocation methods do a sort of much simpler thing, but of course sometimes it makes sense, right? When you really can't afford to spend this much computational cost, you can then go to our collocation methods. So what is a collocation method? So if you consider an ODE like an ordinary differential equation of this type of parameter, so the time derivative of your state is given by a function which is parameterized by p and time with an initial condition u0. The collocation method tries to capture or imitate this function f. So this is so this is like, for example, many people, for example, try to trade neural ODEs like this, but by trying to capture just the right hand side. In the case of a typical neural ODE, you still do use adjoint sensitivity methods, but sometimes you can get away with just using collocation methods, and that's kind of what's going on here. All right. So what exactly is a collocation method? You sort of capture this right hand side function or this time derivative function f by using a estimate of the time derivative from the data, right? And that's kind of and so of course, like you would then find the parameter that matches this f to the estimate that's coming from the data. All right. Simple enough. Okay, so and why is this computationally cheaper, right? The reason is this computationally cheaper is not you're now not integrating across the entire time span. You're just sampling this function f, which is, again, like you need perhaps many hundreds, if not thousands, of these function evaluations, these f function evaluations to do an ODE integration. In this case, you're just directly using those function evaluations to fit the data, which is what makes it much cheaper. You don't do any ODE integration here. But again, all of that depends on how well you estimate this derivative quantity from the data, right? And so as with all things, there are multiple ways to do this. And really, there's just so many different ways to do things, right? And like the purpose of this module is to give a way for you to try all of this. So I'll just go very quickly because we're sort of in the last leg here. Want to quickly go through the three methods. So one's called collocation, the collocation method, which kernel collocation method, I'm sorry. If you want a derivative at this time t, what you do is you go to your data, find some ti, which is in your local neighborhood, and then you sort of construct a polynomial expansion or polynomial approximation for your snapshot yi, where alpha is a vector of polynomial coefficients. You then, as in many polynomial estimation, coefficient estimation algorithms, you use these squares, get the polynomial coefficients, and it turns out that the derivative at time t is the second coefficient, in fact, because this thing starts from 0. And why does that work? Well, there's a reference here at the bottom that you can take a look to understand the math behind why this might work. So I'm going to gloss over this so I can get to the last, so I can get to the model discovery module as well. Okay, so that's the first type of collocation method. We offer two others that do, actually before I do that, there's a reason why this is called kernel collocation, right? So In the least squares method, you have this kernel matrix W, which is basically which calls a kernel, for the time t minus ti, which is the neighborhood point. So you have a scalar function here, and this kernel is like, if you've done all of these kernel support vector machine type exercises, you might understand what this kernel function is. There's Gaussian kernels, exponential kernels, etc., etc. Lots of different kernels that you might employ here. We have a list in our documentation, which again we will send you to. Okay, next. So one thing is you could again use a special estimation method for the derivative. The other thing you can do is you can fit the data to a spline, which is a much simpler way of dealing with this. And once you fit the data with spline, you can then estimate the derivative using the derivative of spline. There is another very interesting noise robust collocation method that we also support. It's called, it's an implementation of the total variational regularized this algorithm called TV diff basically. If you're interested in details for that, you can look at this reference in the bottom here, or check out this Julia package that is an implementation of this out in the open source. Of course, we have secret sauce in this, but these are good starting points for understanding these algorithms. All right. Okay. So the next part that I want to go to, as I see no questions, is to look. Oh, actually, I do see a question. Does the FMU have to provide directional derivatives? For the collocation, no, it doesn't need to provide any directional derivatives, because this thing just estimates the derivatives from data. In a model exchange FMU, to be fair, you do get the right-hand side directly, and that's okay. You don't really need directional derivatives there, like Jacobian or anything. On the collocation method, I will have to get back to you on how exactly that right-hand side is estimated. My guess is we don't support this for these type of collocation methods for simulation FMUs, but of course the team might have come up with something interesting. So I'll have to get back to you on that. Yeah. All right. Can this be done only for parameter estimation? Do we support optimal control? So if you're able to if you're interested in controls, I can point you. In general, I can point you to a separate module. So, for example, our JuliaSim control suite offers a. Quickly go there. Yeah. So if you look at, we offer model predictive control, which is a type of optimal control. I'd say for that's the one that we support. But the other kinds of optimal control, I'd suppose you might have to specify the optimization function and then run it as a model calibration. So you'd calibrate the model plus control system, right? So that's what you might have, that's what you have to do there. But if you want to do MPC, you can just directly do this. There are other kinds of I believe optimal control that this also supports, but I'll have to. I can point you to the JuliaSim documentation on this to see what is supported. Right. The last thing I want to get to is model discovery. Model discovery is a model discovery is a way of let's say you have a model in your data, right? And you know that you haven't captured all the physics, and so, well, how exactly do you discover what those unknown physics are? And so if you've heard of the domain of system identification, for example, especially nonlinear system identification, there's a rich class of methods to take experimental data and then construct a dynamical system based upon the data that you get, which we also support, by the way, classic SysID methods. But in this particular case, supposing you already have a physical model where you haven't captured the data, you can then use data to inform the missing parts of this model. So this is based upon an algorithm that our product head, Dr. Chris Rackauckas, had worked on, called universal differential equations. And this universal differential equations is a way to sort of take your model, augment it with neural network terms, and then essentially run a parameter estimation algorithm where the parameters that you're optimizing for the neural network parameter, right? That's basically a summary of the algorithm. And this, it turns out, has worked for a lot of groups and a lot of people around the world. And of course is one of the core offerings here at the Model Optimizer module. And so what you can do is, if you look at this example here, you have LIGO black hole data that these folks here have acquired. They have relativistic dynamics that they've specified through these equations, but then now they augment this system with a bunch of neural network terms given by F here. And so, can you then learn the parameters P of these functions F, so that you can then excuse me, so that you can then so that you can autocomplete this relativistic model, for example. And this turns out to work quite well. There are lots of interesting cases where this is work, inform structural properties of buildings. There's an example of this with battery models that's very interesting. Battery physics is quite interesting because in many cases you don't quite know all of the physics, especially in degradation, for combinations of new materials and electrolytes and so on and so forth. And so what you can do is you can augment the best possible models that you have with data-driven terms, and then fit those data-driven terms. Well, what's even better is, let's say, is you can then take those data-driven terms and then reinterpret those data-driven terms from a fixed basis of known physical terms. So let me show you what I mean by this. And that's our last demo for today before I will conclude. But let's look at so let's pull up some packages as usual. Pull up some results again, so we don't wait here. And let's pull up an incomplete dynamical system, right? So there's supposed to be another term here. There's supposed to be two other terms here, but we don't know these terms, or we pretend to not know these terms a priori, right, for the purposes of this demo. So what we do again is first we define the incomplete physical model, which we have. Pull some data. Let's take a look at the data. So while this is loading up, I'll just go through the code. So you pull some data up, and then as usual, you define this thing called an experiment. And then as soon as you define the experiment, you define the inverse problem. Now, the interesting thing here is that when you define the inverse problem, you have this new argument here called neural network, right? And one of the neural networks we provide out of the box is a multi-layer feed-forward neural network. There's lots of other options in there, or you could specify your own neural network. And of course, we've initialized this with a custom initializer. But again, we define the inverse problem, and once the inverse problem is done, which should be any minute now, we can then run the calibration. Okay, so one interesting thing about this calibration is that so I see a few questions about resources. I'll send all of these resources to all of our webinar attendees for sure. So the nice interesting thing about this is this optimization is multi-stage. So you see that the first optimization trains this thing with an optimizer called Adam, which is a standard neural network optimizer that's out there. And after 5,000 iterations of Adam, we then go and run about 1,000 iterations of our old friend BFGS. And why do I say old friend BFGS? Let me run a few of these things first. But we what this does, and we'll wait for the plot, but what this does is it lets you go to the ballpark in some sense yeah, as if I can pull up the plot here. So Adam does a pretty good job up to a certain point, but then it sort of saturates, right? And it's hit a local minima. So what do you then do to go to, like, a much better, much better minima, let's say much better local minimum, because you can't say with neural networks, right? You then use BFGS that just like shoots all the way down, which is quite nice. And you can do all sorts of multi-stage stuff in JuliaSim Model Optimizer, which is how we've gotten this to converge. So this is a nice convergence plot. We can plot the results. And with the fit parameters, you can see the parameters fit the data, which is awesome. And then what you can do is we can augment this model, and then, so in this particular case, this is a very simple system, so we know what the missing terms are. So what a nice point of reference is to see how the oops, let this finish, but you see how the UDE has captured the known unknown terms in this particular example. So you see it's pretty much spot on. Having done all of this, you can then run this function called autocomplete, which is pretty cool. Autocomplete needs a basis, so we have a nice little polynomial basis here, and we're gonna use this basis and grab a few terms that most likely fit the data. And at the end here, once we do fit the data with these known terms, right? Like we augment the original system with the discovered terms, and then we look at extrapolation power. So extrapolation power. As you can see, the system is an oscillatory system, and you'll see that even though we needed a little bit of data to capture these unknown physics, this thing keeps chugging, right? And like, even at time spans that tend to 4,000, 5,000 seconds, you can then see that this model is quite usable. So really train once and use many times is kind of how this autocomplete is the promise of this autocomplete thing. And so while we wait for that, I will look at if I have anything else to get to. I don't think I do. But yeah, once this is probably going to take a minute. But really, what I like about this is just the ability for these neural network terms to be then physically interpretable again, which is pretty important for for obvious reasons. Yes. So as you can see here, we've trained this, we fit this thing to a bunch of data in like this time frame, but then the augmented model with the discovered terms keeps chugging away, which is pretty awesome. Yeah, so that's roughly all I have for you guys today. But yeah, just to recap, JuliaSim is our modeling and simulation product. We went over the capabilities of Model Optimizer, which is a component of JuliaSim, where you can calibrate models to data as well as discover new and unknown physics, or missing physics, let's say. With that, perhaps we'll take a few more questions, Misha. Is that a?
I think we can squeeze it in.
Yeah.
There is a question of, does the model discovery support neural IPDE?
Neural PDE? Well, so with pins, do you mean? So neural PDE is pins, I'd say. Just for physics informed neural networks. So the tentative answer is no. But of course, but if you mean, but if your question is, well, can I then add these unknown terms to PDE equations? We have it. Yeah, you can absolutely do that. So I'd say that's how I would answer if I understand your question correctly.
Okay. How can I start using this? Is
Yes.
the other question here.
Well, the easiest answer is get in touch with us. At the moment, we do have a free tier on the way. where we will give you access to the environment and everything. But right now, we provide access on request. So if this is something that you're looking to use in your work, we would love to hear from you, get in touch. And my inbox is always open, and I'm always happy to talk to folks. Misha, do we just follow up with an email sending all the links?
Yeah, so we will
Yeah.
follow up in 24 to 48 hours with an email that
Yeah.
will have a link to the recording, as well as a collection of things that Ranjan's mentioned in the webinar that will include links to as well. So expect to see that in your inbox.
Yeah.
Okay, given we don't have any more questions and we've run a little bit over, I'm going to thank you, Ranjan, very much for presenting. And thanks to all the attendees who joined us today. It was a pleasure having you. We look forward to seeing you on the next webinar. Thanks, everybody.
Thanks, everyone. Take care.